Okay. The floor is yours, Jan.
Thank you. Hello, my name is Jan Gorecki. Uh, I started to use data table 11 years ago. Then 9 years ago, I submitted first pull request to its code base, and over time, I contributed more and more. And it happens now I'm one of the most active contributors to the package. And I want to share some of the useful info for users that may not know data table yet. My talk will be very kind of introductory focused. So I will focus initially on syntax because this is where when data table was created, it was not meant to differ much from base R. So in package description from 2008, we can see that data table was just meant to be a data frame without repetition of the data frame object name. So we can directly use variable names when selecting rows and selecting columns. And additionally, the join syntax was added to cover base merge functionality. And focus was just to make a data table like more user-friendly, not strictly faster as it end up over years. So here is example of using data table comparing to data frame and how it actually uses base subset feature inside square bracket operator. When we use data frame square bracket operator, we of course has to prefix variable name with the object name. There is function subset which removes this need, and we can do this operation without repeating name of the data frame. And in data table, we have it built in. So there is less to type. Then similarly, when selecting columns, in base R data frame, we don't have to provide the name of data frame, but we have to provide vector of the names, and we cannot really do anything else with them. We can just subset column names and then on top of it call some function. If we will use with function, then we are able to do some operation directly on the variable names. So data table plugged in this with functionality inside the square bracket, so we can directly operate on variable names inside square brackets. In next examples, it will be much easier to see why it's so practical. Of course, this row selection and column selection works together. So here already we can see how much simpler code is getting when we have to do both this operation. In data table, it's like much, not only less to type, but also more clear to read what is happening. And now let's stop a little bit on the first argument to square bracket. Its name is I. And there are few operations that we can do there. We can subset rows by providing expression. This expression has to evaluate to logical vector, same like in data frame. We can sort data. It's also the same like in data frame. In data frame, we would have to obviously use the like data frame name in the order function. We can as well filter against the aggregated value. It's like in SQL language, it will be having. So this to make this in data frame, it wouldn't be very different. We would have to prefix both variable names with the data frame name. And we can also join, but this I will cover in another slide. Now the second argument to square bracket method. At start, maybe I will mention that it's usually expected to get a data table on the return from our operation. That's why we will try to have this J argument to evaluate to a list. Because if it evaluates to a vector, then and not a list, then we basically are getting a vector. In the first example, it's just scalar vector because we aggregate all data table. And in the second example, we see how we can calculate the same but retain the class, that its results are still data table. Third example shows alias that we use, which is the dot symbol. It's basically the same as using list. So it's just less typing and less to read as well. So third example shows how we can do two aggregate function at once, just by supplying list to J argument. There is another feature in J which is used with the valorous operator. This operator is typed by colon and equal sign. And I will talk a little bit more about updating in place in the next slides. Now I just want to present how we can use this in data table to change object. What is useful here to note that when we use this operator, we don't assign results to a new variable, because the object that we are calling this function on will be updated in place. So here we will multiply one of the columns by 2 times, and in the first line, and then second line just calculate means. So as we can see, it's like twice more than in the previous slide. And the same way we will divide this column later on, and we are again receiving the previous value back. So this is another use that we can do in the J argument. Now I would compare how it looks like when we try to make some more complex query in base R using data frame, and how it will look in data table. So here we are, we want to aggregate and calculate mean for in the data frame empty cars, where column AM is equal to 1. And this filter for this, and we want to calculate mean of the MPG column. So this filter on AM column we have to apply multiple times. It's not only more to type actually, but also this has to be like evaluated twice. So some parts of these queries are unnecessarily calculating the same information to resolve this expression to a logical vector, so it can perform subset on expected rows that we want to use. So here we see it's 89 characters and 41 is actually repeated. And in data table, it's quite compact. It's 27 characters, 4 is repeated. And we can see that we apply filter once. Again, we don't have to put a name of the data set in the front. so it's less repetition as well. Then we put aggregate function and just a column that we are grouping by. So we can see that it's like more than 3 times more efficient in terms of reading and writing, and also understanding what is written. Now we are going back to joins. Here is some code that whoever wants can run to reproduce this example. And we have two data tables and we will be joining them. Joins in data table were implemented as a subset. It's basically how the subset works in R. When we subset even a vector, not necessarily data frame, we are doing right outer join on that vector we are subsetting. So if we subset by values that doesn't exist in the vector that we are subsetting, we will still get them in the results. I don't have an example presenting a vector here, but that's how base are designed, subsetting with square bracket. It's basically right outer join. This here corresponds to the argument al.y equals true, which defines that this has to be right outer join. So in data table, joins are made by basically in the I argument of square bracket, we provide the second data table, and using on argument, we specify columns. It can be specified as unquoted variable names and also character vector as well. And corresponding statement in base R would look like the bottom one. So here perform join of data table A and data table B on column ID and code, and whatever ID and code will be present in B data table will be present in the results. We could do an inner join, of course, as well, providing no match argument equals to null. By default, no match arguments is equal to NA. That's why it's outer join. This terminology is heavily used in SQL, and that's from where this kind of standard naming came from that I'm using. Now, one slide of the recap of the arguments in the square bracket method, how we are using them. So first, it's called I. We can subset, order, filter using aggregated, so having, and we can join. Then second one is J. We can select or update some columns. And third one is by. It is used to specify grouping variables. There are many more arguments there. It's just those three are the basic, the most commonly used one. Another slide explaining joins, and here they are combined with the values operator to update a table in place. So in this situation, we are updating table in place, taking the data from another table. We join two tables, and instead of generating some result, new table, we just take out rows. We just take out the value of mul column from second table, and we use it as an operation to transform the data that are already in our first data table. So we again join on ID and code column and change column val A to be val A times mul. So it can be some multiplier value that was meant to be used, and it's specified for each ID and code. And then another example of join is to aggregate while join. And in this situation, it's basically shortcut, which often it's very useful because it doesn't materialize results. Normally we would join tables and then do aggregation. And if the join is resulting more than 2 billion rows, or we don't have enough memory, then it will not finish. Using aggregate while join, we can compute many operations that normally wouldn't be possible without this due to memory limits. So it will basically, for each matching ID and code, it will compute the G argument, and it will not make it all at once, but for each group separately. That's why it can still fit into memory. If we first have to join data and then do this aggregation, then we has to kind of materialize this join data. With this aggregate while join, we are skipping this materialization of the join tables. And this is very useful, especially when we are using non-equi-joins, because then materialization of this table can be very big. So with this dot each I, in the by argument, we can skip it and perform aggregation directly during join. And the third join mentioned here is combination of both. We can update some table in place using data from another table and aggregating at the same time using dot each I provided to by argument. And last slides on join. This is already not reproducible with the previous objects. So few examples of non-equi join when we want to match data from some events to predefined periods. And here we can see syntax of the non-equi join. There is also support for this syntax provided in character string. So in case we want to programmatically define if it should be greater or equal or smaller or equal, then we can use character strings for easier creating this argument. Another joints are rolling joints. These are already for a very long time in data table. When I came there, it was already there. It's joining for not if there is no matching rows to some values, then it will match to the next matching row. So this is very useful when we have some two data sets which are not exactly matching, like website sessions and payments. So we can then match by like username and time. So we can see which sessions were ending up on the payments rows. And another type of joins is overlapping range joins. It was implemented quite a long time ago and heavily used in genomic intervals. It's kind of in bioconductor there is a function find interval, which is very commonly used. So this was developed to be faster replacement of that because one of the main developers just needed it for his work. We've seen some few special symbols already in those slides, and now I would like to focus on those. So each I was the one that recently we've seen that it's used in, we already seen only each I. So we use it in by to aggregate by each matching I rows during a join. Then dot, those will be soon presented in the next slide, so maybe I will not talk too much about them. It's number of rows, like total number of rows. Then SD basically stands for the self. If we want to just reference self, we can use .sd. Group is represent the counter of the current group when we are grouping, and GRP represent total number of groups, by represent current grouping variables, and I represent integer index of a row within data table. And we have a manual which describes them more in details. So let's go to some other examples. We have .n symbol, and now will be example why it's useful, basically, because there are cases where it's really makes sense. We have one data table that has 10 million rows, 4 columns, another 2 million rows, 1 column, and some different ways how to calculate how many rows will merge produce. So using base R, to calculate how many rows will be on the result, we need to wait 83 seconds, and it uses 5 gigabyte of the memory. Then using data table, the similar way, basically doing a join and then checking how many rows were on the result. It's 1.3 seconds and 1 gigabyte of memory. Then the traditional way, if we wouldn't have .n symbol, we would just use length of a column. It's little less below second and 0.6 gigabyte. And then .n symbol, it's even faster and less memory, because we don't have to materialize the ID column. Data table will know that we are not selecting any columns. We are only interested in a row count. So it doesn't have to materialize ID to check how long it is. So as we can see, it's in some cases, it makes difference, because if we don't have enough memory, it will just crash and we don't have any results at all. Then SD is a placeholder for cells, like it's kind of select star from SQL. Here are a few examples that of the SD usage. Because in J we expect to have a list, we can use lapply, which on each column can apply a min, like in the second line. And here we apply grouping by species. Here it's good to mention that when we use SD and by argument, it automatically excludes columns that are used in by from the SD. So the min will not be applied on species column. It only for other columns of iris data table. And because J likes list, we can easily use whatever function we want to just still have a list. So in the third statement, we calculate min for all columns, and we calculate max for all columns. And those two results are list, and with C function, we just combine them in the single list. And then there is also another argument, SD calls, which can be used to subset columns which we are interested in SD. So this way we can, instead of taking all columns like other than by argument, we can explicitly provide which columns we want to have in SD placeholder. And now some more examples of the dot symbols. Here is quite, it's also, this code also shows how flexible is J argument. It's the same in I argument. This curly brackets that we see here, it's an expression, multi-line expression that evaluates to a list. On the very last line, we can see that it's a list which has a name and equal to a value. So, and in this multi-line expression, we can basically calculate whatever we want. So I presenting here the way that let's make grouping with some debugging. In first line, we are just printing to console. We are using by special variable and column species. Only this column is available in .by argument because this is what we are grouping by. And this first line is, as a result, we are getting this output up to the dots, basically, because this is what we define here. Then we are calculating the temporary variable, which is the sum of squares of two variable in the data table. Then we just make a sleep for 1 second to not be too fast. And then we calculate mean of square root of the temporary variable. So what we are basically calculating as ans is the mean sepal hypotenuse. And also there is another cut. The previous one didn't have new line character at the end. That's why the second one is still printed in the same line. And we could basically wrote even here catch system time and then print how long it took to calculate this particular group. But here we use the .grp symbol and ngrp to just specify which group was done and how many groups were there. So those variables here are presented in this context of multi-line expressions. So, and there is deep flexibility here. We can just call databases, we can use other packages, we can use whatever we want, write to flat files, like whatever we want, we can just put in these long multi-line expressions. So this is the magic number 1. Then magic number 2 is a new argument that was just released a few days ago in the CRAN version of data table. It's basically a way to specify whatever there is in I, j, and by a variable like character variables. So we will modify the previous example, but we want to be able to specify which what will be the grouping variable by a string, what will be the variables used in the calculation, if it will be sepal length or some other, what will be function used as well, and what will be the output column name and how long will be syslib function waiting for. So for this purpose, there is new env argument in data table that basically takes a list and specify when we provide the character scalar to some variable, then those variables are basically substituted. So you can see that grp variable, we provide species, and here we can see there is grp variable, and another time it's here. So in those two places, instead of having grp, we'll have species, and not actually character scalar, but it will be unquoted species. So here character scalar would work, but here if we would just substitute into character scalar, it wouldn't work. So it will be unquoted variable name species. Then variable 1, variable 2, we are using to calculate temp variable. So instead of those two, we'll have unquoted variable names. Then a nap is just this number, which will be substituted. And then we have a function here, which will be substituted into unquoted function name mean. And output column name, yeah. And those will be all calculated. So this query will give exactly the same output as this. We can use also in data table, there is argument verbose. If we provide verbose true, we will get some extra debugging information. and we will see how the substituted query looks like. So we can ensure that all the substitution that we expected to have is as it meant to be. And this is especially useful. I remember I was struggling to kind of make my queries to data table more flexible when I was developing Shiny application to kind of aggregate, and I needed to very flexibly define which columns, which function, and so on. And it was not very easy. So this env argument I developed some time ago, and it's available since few days on cron. And there may be some bugs, of course, because it just landed on cron. So whatever will be not clear, if you have any questions, you can as well. There were already few questions. So far, no bug. You can submit to data table issue tracker to find out how something has to be done or if it's working as it's meant to be. Then another magic that I mentioned before about the Walrus operator is reference semantic. And here I will just shortly elaborate why it matters, basically. Sometimes the thing is that it reduces memory footprint. And why memory is important? Because if we don't have enough memory, we will not get any answer at all. And then even slow answer is better than no answer. So if we don't have enough memory, we have to go to databases or on disk formats, which most often will be slower, not always, but most often will be slower. And we will have to employ another tool in our tool stack. So how we use reference semantic in data table, it's either by set functions. There are multiple, it's set keys, set order, set dt, and few others, or Walrus operator, and recently also added alias to it, let function. So those will be updating data table in place instead of calculating the results as a new object. So when it matters, here is example that we have 50 million 50 million rows, 26 numeric columns, and it's almost 10 gigabyte just data frame. If we want to sort it by 3 columns, data frame will get killed. If we want to turn it into data table, because it's on my laptop, which has 16 gigabyte, right? So it was 10 gigabyte. And to sort it, basically, this means that the right side already occupies 10 gigabyte, and sorted one would occupy another one. So it's not enough, so it get killed. Same with using as data table. This object still will exist as a separate object, so we don't have enough memory to create new one. And that's why there is setDT that updates the object that was already present instead of making copy. And then we can do set order and sort this object by 3 columns. And that works on my laptop where I had 16 GB of memory. So there are cases where it matters. It's yeah. Then there are some traps about this, of course, because with great power comes some responsibility. So we don't use when we update in place, like here, set dt, set order, we don't assign to new variables. And when we assign to new variable, R is not making a copy, it just refers to other object and increments some reference count. So we can end up being surprised in multiple cases. So we have some iris data table with 5 columns. We create one object dt2 and another object dt2. The difference that dt3 is a deep copy, so it's not just referring to other object. Before update, we will be updating DT object. So we see that DT2 has 5 columns, and after updating DT, also DT2 has more columns. So DT2 got updated as well as DT. So because it's just reference to DT. So DT2 will be, if we update DT in place, then DT2 will be also updated. And DT3, because we made the deep copy, it stays and has 5 columns. Another traps, it's that names function doesn't copy, it also refers. So it's very similar example. We have nm1, nm2. We update dt to create new column, and name one variable got extended. It's a character variable, but it got extended. It's now longer just by changing our data table. And nm2 variable stays the same because it was a deep copy of the character variable. This is probably the biggest surprise, and there are some ideas to change this behavior, but because a lot of code depends on that, it will happen in some 2.0 version, which probably will take some time. So it's good to be aware, and whenever using names, this is the same as it is a surprise. It can be a feature, because if we add new columns, we don't have to update our names variable. It's already updated. And then another magic here is that data table uses multiple cores. In the square bracket, some operation uses multiple cores, so it's not scaling that well as examples that I choose here. But over time, we hope that more and more operation will be inside using multiple cores. And here are some few examples I found in the news file when some functions have been implemented. So here was example of using default 4 cores, and we have 300 million true or false values, and it's 1 gigabyte variable. And there is some benchmark using base R, dplyr, H utils, and data table, 3 different types using single thread, 2 threads, or 4 threads. So we can see that it scales pretty well. From 1.4, it goes 0.4. So the more threads we throw on this, if we have machine that has 128 threads, and we have some big vector or some logical expression, then it will scale very well. Another example, it's from a function meant to fill missing values by using last observation, or it also supports next observation. But here we have last observation. We have 10 million rows and 100 columns. It's 7.5 gigabyte. The most popular package for this purpose is zoo, and using that function, it takes 53 seconds. Using single thread, and in data table, it's not by reference, it's just creating new object. We have 7 seconds. Using 40 threads, we go to almost half seconds, and we can also do this by reference. So we change the object in place by changing those NA values, and this goes even lower. So we can see that without data table, we stay at 53 seconds, and in data table, we go far below a second. And last example of multi-core usage is my functions that I implemented that basically calculates rolling mean, and they accept vectorized input. So we can provide multiple columns and specify multiple rolling window sizes. So in this situation, we have a list or a data table, because data table and as well data frame are just lists with some extra attributes. So we have a list of two vectors of 100 million rows. And we want to calculate rolling mean over last 1,000 elements and 10,000 elements. So having just a single thread, it needs 2 seconds. If we use 4 threads, then it very well scales to half a second. And there is a lot more that was not covered in these slides, especially function for reading, writing. These are very fast and basically many other libraries, and not in R, but in general, competing and struggling to catch up with the speed of those. Both are very use multiple threads and have a lot of features. There are other functions for reshaping data from long to wide formats and back. There are 3 functions for, these are basically wrappers on the grouping. So they come from SQL, basically, were designed after SQL. If we want to have some subtotals and grand totals by grouping variables, instead of specifying these multiple grouping queries, we can just use rollup or cube or grouping sets to have those subtotals calculated in the single query. Then set operators, which can be used to compare which rows are missing from one data set to another, or check if two data sets are equal, and also fast rolling functions, and many other smaller functions that are just helpers to like faster version of switch, if else, rank, sort. And the last magic is that data table has no dependencies, and it's generally easy to do a lot and to do it fast if you use dependency, because we can just find what is there that it's good, fast, and we have it for free without, we just put import some package, and it's already fast. The trade-off is that dependencies are invitations for other people to break your package. So when you have a dependency, you are basically responsible for fixing whatever is there. It's not always that clear, but there is no guarantees, basically. That's the thing. And in data table, we implement all the functionality on our own, with small exception that fast reading and writing to a file, only compressed one. So if we want to use compressed file, then we use some optional dependencies, which are not needed for package installation, of course. Yes, and now I wanted to thank for this meeting, for Sevilla Earth for hosting, for organizers, and for Toby Hawking for reviving data table, because it was not very active for 3 years, and Toby managed to find some foundation that sponsor some activities, and one of those activities is sponsoring travel, which sponsor my travel here, and also for you to listen to my talk. If there are any questions, I'm happy to answer those.
Just question about the number of threads. I suppose, I assume that it always use the maximum number of threads available, or you need to fix it in manually?
Number of threads. That's the sensitive thing, because CRAN allows only, during check, allows only 2. Initially, data table used all, but many users reported, and we also noticed that there is not big difference between using half and all. There is usually some speed up, but it's not from 1 to half. It's basically much bigger speed up. So we decided to use half of the CPU. So here we can see that the default 4 threads on a machine that has 8 logical CPUs.
So the default is the half of the...
Yes, yes. This can be easily configured using setDT function, setDT threads, can be configured using environment variable, can be configured, also respects OpenMP and environment variables, which on clusters are standard way to limit how many threads should processes use. So by default, it's half, and it's quite good, good optimum.
Thank you.
Any other question?
Yeah, so well, I have a few questions.
Yeah, very good.
Some of them we can talk over the beer afterwards. So why is it so fast? I understand it's very memory efficient because you are it's very clever, very smart on how to manage all the objects. And speed only comes from that efficiency in choosing what to do with the object, or also on, I mean, is there a lot of C inside, or is it mostly base R, or what's inside that table?
So it's basically 95% will be C.
Right.
Yeah, and that's where the speed comes from. And it's not just from C, actually. It comes from the algorithms implemented, because, like, for example, sorting algorithms had many iterations in data table when it was improved, and it ended up to be, there are some slides that this sorting in data table beats some Intel TBB, which is like multi-threaded sorting algorithm, beats it very badly. So the algorithms, some algorithms, not all, but some are, so it's like a masterpiece, this sorting, that it's just like was developed over years in multiple iteration and got really, really fast. Behind this sorting, it's radix sort, which was generally, you can still read online that it's good for integers and not for other types, but in recent years it was like proven that it's good for everything. And this is what Matt Dole and Arun Srinivasan implemented in data table. They also contributed this to base R in 3.4 or 3.5 version, but in base R, the version is not, it's single threaded. Later on, they added multi-threading to this. So this sorting, it's really very well made. And this also comes not only from knowing C, but knowing the RC API. For example, there are some attributes on the C level that are not being used, and you can use them to speed up some operation, to carry some data together and reuse that data. And this was some tricks that Matt Dole was using. And then they also started to use it in base R, because it's there, it's not used, so can be used for that purpose. So it's The first version, I'm pretty sure, was only R, because R is very flexible on this computing on the language to, in square bracket, catch what user wrote there and just find the proper scope and stuff like that. But it's already in 2 years will be 20 years when data table started, so it got a lot of code over time.
Well, there is a question online,
Yeah.
Jan. Carlos Ortega from the Madrid user group has a few questions. I will try to to translate you a few of them. One is in the latest version 1.15,
Yeah.
you've included the ability to use changes per column, he's saying, using by equals dot y. I. If you could comment on these last changes.
Changes, but I'm not sure which exactly feature he is referring. Dot by equal
Dot I
equal to what?
Is by something.
Yes. So yeah, I remember.
Per row, sorry.
Yeah. So
Changes per row.
if someone would like to evaluate expression in the G argument, so the one that we select columns, by each row of the data table. So basically, we would like to, like in by, we specify groups of rows, and we calculate J argument for that. So if we specify by equals dot I, then for each single row will be like a group, and then resulting will be a computation that J will be computed for each single row. So, and I don't think there will be much speed up there, because it's just on the R level. It's just convenience that user don't have to write loop or do some other tricks.
Another question is, the collapse package is starting to offer speeds faster or similar to data table. Is there some type of collaboration that can be established or something like that?
I'm not sure, because the first thing is that like collapse, when it started, was like taken some code base of data table and put some more stuff, and the stuff that it added later was in C++, and in data table we use only C because it's much faster. Compilation time can be easy, like easily 50 times faster than some packages takes 70 minutes to compile, like DuckDB, for example. And if you keep stuff in C, it's still in seconds, basically. So collapse is a nice extension, let's say. It provides many fast functions, but it also, in many places, use different algorithms. So we don't use hashing in data table for finding groups. In collapse, I think that's the case. And in this situation, there are different cases where it can scale better. There will be many situations that collapse can scale better, but there will be situations that data table will scale better, just because the different algorithms may apply in the different situation. Like, for example, how many unique values we are grouping by. If there are only 10 groups, or there is 10 million groups. And when there are more groups, then hashing will not be that good scenario. So if we have very few groups, then hashing will be faster. If we have many groups, then hashing will be slower.
And well, one last, and we will close the session. He's asking about the relationship with Python and the data table development in Python. Is there any
So
relation?
there is relation, basically. Data table in Python was developed by H2O, and Matt Dole, the main author of data table, was mentoring this development for some time. Later on, he was, as far as I know, was not mentoring this development. And that Python package was focused on supplying, it was a dependency of the H2 or machine learning software. So there were some machine learning functions as well, which we in our data table we are not really focused on. So there were some ideas to make some parts of code common for Freed, for example, but in the end it didn't work out because it ended up to be just more effort than just having like recreating code in one place than another, than just having some components that has to be shared.
And what's your favorite deeply implementation?
What implementation?
He's saying something. I assume that deplete, tidy table,
Yeah.
clear, tidy table were. Which one is going to
I never use those, so I'm not good person to ask. It's like I miss that there is not a reverse package because I so in love with the syntax that data table use that whatever comes there, like DuckDB, Polars, these are like amazing new tools. But for me, it's just inconvenient to write so much to solve problems. I just want to read and write fast, and so I hope at some point there will be some reverse process that we can use syntax from data table and use it on the other backends.
Well, I think we can close the session now. Thanks so much,
Thank
Jan,
you.
for coming. It's a pleasure to have you here.
Thank you.
And that's all. That's a wrap. Let's go for the good part. For the good part. Luego. Bueno, decirle al chaval.
Si quieres.
Voy cerrando y tirando para allá si queréis.